In this video, we'll study how to solve second order homogeneous linear differential equations with constant coefficients, and then we'll study natural oscillations, oscillations with damping, and forced oscillations. Now in first order differential equation, we know that a linear equation in y is represented by dy by dx plus pxy, and it is equal to qx, or we can write y dash plus pxy, and it is equal to q as a function of x. And we know how to solve it. For this, we take an integrating factor, which is e to the power integration of p dx, and then we write this solution as y into e to the power integration of p dx, and it will be equal to this integral q into this integrating factor e to the power p dx and plus c. This is how we solve linear differential equation in order 1. Now, if we look at linear differential equation in order 2, this equation can be expressed as y double dash plus pxy dash plus qxy, and it is equal to some r as a function of x. Now this equation is linear differential equation in second order. Now if in this linear differential equation we take this rx as 0, then the equation we'll get is y double dash plus pxy dash plus qx, y equals to 0, and this equation is second order homogeneous linear differential equation. So it is homogeneous linear differential equation in order 2. Now if we take these functions px and qx as constants, then we can write this differential equation as y double dash plus ay dash plus by equals to 0, and this differential equation is homogeneous linear differential equation in order 2 with constant coefficients. So basically in this video, we'll be solving such questions. Now this differential equation, it is very important in mathematics as well as physics and engineering applications. So we'll study it in a lot of mechanical and electrical vibrations. Now we'll learn how to solve this differential equation. Now we know that a homogeneous differential equation in first order, y dash plus ay equals to 0, it will have a solution of the form e to the power minus ax. So basically from here we get an idea that maybe one of the solution to this equation is y equals e to the power lambda x. So what we'll do is we'll substitute this y in this equation and we'll try and find value of lambda. Now y dash will be lambda e to the power lambda x, and y double dash, it will be lambda square e to the power lambda x. Now if we plug in all the three values, then we can write lambda square plus a lambda plus b equals to 0, and this equation in lambda is called as characteristic equation. So for this homogeneous second order linear differential equation with constant coefficients, we'll find this characteristic equation, and if we solve this characteristic equation, we'll get two values of lambda. So values of lambda will be minus a plus minus under root of a square minus 4b upon 2. So suppose one of the values is lambda 1, which is minus a plus under root of a square minus 4b by 2, and we have lambda 2, which is minus a minus under root of a square minus 4b by 2. Now depending on this discriminant, a square minus 4b, we'll have three cases. Case 1, when it has two distinct roots. Case 2, when it has two equal roots, and this third case when it has a complex root. So we'll deal with the three cases. Now in case 1, when we have two distinct roots, lambda 1, lambda 2, when a square minus 4b, it is greater than 0. Now in this case, we'll have two solutions, and which are e to the power lambda 1x and y2, which is e to the power lambda 2x. Now these two solutions, they are linearly independent solutions. And because these solutions are linearly independent, they become a basis of a solution. So we have e to the power lambda 1x and e to the power lambda 2x. So from linearity principle or from superposition principle, we can say that solution to this differential equation is this y, some c1 y1 plus c2 y2. So we can write solution to this linear differential equation as y equals c1 e to the power lambda 1x plus c2 into e to the power lambda 2x. So this is the solution of this equation when discriminant is greater than 0. So if we take an example, suppose we have a differential equation which is, now if we take this solution as e to the power lambda x, we can write its characteristic equation as lambda square plus lambda minus 2 equals 0. Now we can factorize this as lambda plus 2, lambda minus 1 equals 0. That is, value of lambda is either minus 2 or value of lambda is 1. So we have lambda 1 as minus 2 and lambda 2 as 1. So we have two real and distinct roots. So now we can write its general solution as y equals c1 e to the power minus 2x plus c2 into e to the power x. And that is the answer to this question. Now we'll take up this second case when the roots are real and equal. Now if the roots are real and equal, in that case, a square minus 4b, it is equal to 0. So in this case, we have lambda equals lambda 1 equals lambda 2, and it will be equal to minus a by 2. So we get one of the solution, and one of the solution is y1 equals e to the power minus a by 2x. Now challenge in this question is how to find this other solution. Now in this case, one of the solution is known. We need to find another solution to obtain a basis, and for this we'll use a technique called as reduction of order. So what we'll do is we'll set that y2 is u into y1. Now we need to determine this function u. Now y2 dash, it will be u y1 dash plus u dash y1, and y2 double dash, it will be u y1 double dash plus u dash y1 dash plus u dash y1 dash plus u double dash y1, or we can write this as u y1 double dash plus 2 u dash y1 dash plus u double dash y1, and that's your y2 double dash. Now this solution, it must satisfy the equation. So we'll get y2 double dash plus a y2 dash plus b y2 equals 0. Now y2 double dash is u y1 double dash plus 2 u dash y1 dash plus u double dash y1 plus a, and y2 dash is u y1 dash plus u dash y1 plus b, and y2 is u y1, and it is equal to 0. Now we'll collect terms of u double dash, u dash and u. So it will be this y1 into u double dash plus 2y1 dash plus a y1 u dash plus u into y1 double dash a y1 dash plus b y1 equals 0. Now basically y1 is solution to this differential equation. So y1 double dash plus a y1 dash plus b y1, it is equal to 0. And we also know that this y1 is e to the power minus a by 2x. Now we differentiate this, we'll write y1 dash as minus a by 2 e to the power minus a by 2x, and e to the power minus a by 2x is y1. So we'll get 2y1 dash plus a y1, it must be 0. That means this part is also 0. So from here what we'll get is u double dash, it is equal to 0. Now if u double dash is 0, then u dash is some constant, say c2, and u is c1 plus c2x. Now once we have this u, we can write solution to this equation, and solution to this equation is y equals u into y1. So it will be this c1 plus c2x into e to the power minus a by 2x, and that is the solution to this differential equation when we have two real and equal roots. Now say for example, suppose we have this equation y double dash plus 8y dash plus 16y equals 0. Now we can write its characteristic equation as lambda square plus 8 lambda plus 16 equals 0. That means value of lambda is minus 4. Now once we have this lambda, we can write this solution as y equals c1 plus c2x into e to the power minus 4x. And that is the answer to this question. Now we'll take up this third case when a square minus 4b is less than 0. That is when we have complex conjugate roots. And in this case we'll have lambda 1 as minus a plus under root of a square minus 4b by 2. Now we can write this as minus a by 2, and since we know a square minus 4b is negative, we'll take this 2 inside and we'll take minus 1 common. So it will be under root of b minus a square by 4 iota, and the same we can write lambda 2 as minus a minus under root of a square minus 4b by 2, which is minus a by 2 minus under root of b minus a square by 4 iota. Now what we'll do is we'll let this under root of b minus a square by 4 as some omega. So now we can write this lambda 1 as minus a by 2 plus iota omega, and lambda 2 will be minus a by 2 minus iota omega. Now using this we can write two bases. So it will be e to the power lambda 1 x, which is e to the power minus a by 2 plus iota omega x, which will be e to the power minus ax by 2 into e to the power iota omega x, which is e to the power minus ax by 2 into cos omega x plus iota sine omega x. In the same way we can write e to the power lambda 2x, and it will be e to the power minus a by 2 minus iota omega x, and it will be e to the power minus ax by 2, and here it will be e to the power minus iota omega x, which is cos omega x minus iota sine omega x. Now, looking at these two solutions, we can say these two solutions can be formed with two linearly independent solutions, which are, say, y1 e to the power minus ax by 2 cos wx, and y2, which is e to the power minus ax by 2 into sin omega x. So we can write this general solution as e to the power minus ax by 2 into a cos omega x plus b sin omega x. And this is the solution to this equation in this third case when we have complex roots. Now say for example, we are given that y double dash plus omega square y, it is equal to 0. We'll get lambda square plus omega square equals to 0 as characteristic equation. So here lambda will be plus or minus iota omega. So in this case, this y will be e to the power 0x into a cos omega t plus b sin omega t, or solution to this equation will be y equals a cos omega t plus b sin omega t. Now we'll discuss spring mass model. So we have the spring which is attached to a mass, say m. Now in this state, the system is in static equilibrium where gravity is balanced by extension in the string. Now at this state, suppose we displace this mass by a vertical displacement y, then the spring force minus ky, it will act on the system, and this force, it is represented by my double dash, or we can write this as my double dash plus ky equals 0, which is homogeneous linear differential equation in order 2 with constant coefficients. Now if we write its characteristic equation, it will be m lambda square plus k equals 0, or lambda equals plus minus under root k by m. Now suppose this under root k by m is plus or minus omega naught. From here you can write its general solution y as a function of t as a cos omega naught t plus b sin omega naught t, where omega naught is under root of k by m. This is the case of undamped oscillations, and this motion is called as harmonic oscillations. Now if we want, we can also write this as under root of a square plus b square, and we write this as a upon under root of a square plus b square cos omega naught t plus b upon under root of a square plus b square sin omega naught t. Now if we take this as sum cos delta and this as sum sin delta, we can write this general solution as yt equals a naught cos omega naught t minus delta, where a naught is under root of a square plus b square, and tan delta, it is equal to b by a, which basically is a shifted cosine curve. Now what we'll do is we'll add damping in the system. And here what we'll assume is, we'll assume that this damping force, it is proportional to velocity of the system, y dash. And because velocities are generally very small, it is a very good approximation. So in this case, we'll say this damping force, it is given by minus c y dash. Now with this damping force, this mechanical system can be expressed by this second order differential equation as m by double dash, and it is equal to minus this spring force and this damping force. So we can write this as my double dash plus cy dash plus ky equals 0. Now we'll write its corresponding characteristic equation. So it will be m lambda square plus c lambda plus k equals 0. So from here we can write this lambda is minus c plus minus under root of c square minus 4km upon 2m, which is minus c upon 2m plus minus 1 upon 2m under root of c square minus 4km. Now here we'll use a short notation. We'll let alpha as c by 2m and beta as 1 upon 2m under root of c square minus 4km. So now we can write this lambda 1 as minus alpha plus beta and lambda 2 as minus alpha minus beta. Now again, depending on this value of c square minus 4km, we'll have three separate cases. Case 1, when c square minus 4km, it is greater than 0. In this case, we'll have two distinct roots, lambda 1 and lambda 2, and this is the case of overdamping. And then the second case where c square minus 4km equals 0. Here we'll have a double root, and this is the case of critical damping. And finally we have this third case when c square minus 4km, it is less than 0, and in this case the roots are complex conjugates. And this is the case of underdamping. So depending on the discriminant of this equation, we'll have three cases of overdamping, critical damping and underdamping. Now we'll discuss this first case of overdamping. So in this case 1, where we have c square minus 4km as greater than 0, we'll have overdamping, and in case of overdamping, we'll have this solution as yt equals c1 e to the power lambda 1t plus c2 e to the power lambda 2t, where lambda 1 is minus alpha plus beta and lambda 2 is minus alpha minus beta. So it will be this c1 e to the power minus and then alpha minus beta t and plus c2 e to the power minus alpha plus beta t. Now typical motion in overdamped case, it is represented by these three lines 1, 2 and 3, and in all these cases we have taken positive initial displacement, and in the first case we have taken positive velocity, in the second case we have taken zero velocity, and in the third case we have taken negative velocity. So this is the general motion in the overdamped case. Now we'll take on this second case of critical damping. Now in this second case, when c square equals 4mk, where we have condition of critical damping, in this case both lambda 1 and lambda 2, they are equal to minus alpha and value of beta is 0. So for this case, its displacement is represented by C1 plus C2t into e to the power minus alpha t. So displacement in the case of critical damping, it is given by this equation. Now for different values of C1 and C2, if we consider its typical graph, if we take positive initial velocity, then its motion will look like this first dotted line. If we take V as 0, it will be the second dotted line. And if we take V negative, then the motion will be along either of these two lines depending on values of C1 and C2. Now essentially this first case of overdamping, it is non-oscillatory motion, and this third case of underdamping is oscillations. So basically this case, C square is equal to 4 mk, it marks the border between non-oscillatory motion in overdamping and oscillatory motion in underdamping, and that's why we call this as a critical case. Now we'll come to its third case, which is case of underdamping. Now in this third case of underdamping, the condition we have is C square minus 4 mk, it is less than 0. And if C square minus 4 mk is less than 0, what we'll do is we'll know that this beta, which is under root of C square minus 4 mk, will be purely imaginary. So we'll assume that it is equal to some iota into omega star. So for this case, we'll have two values of lambda. It will be minus alpha plus iota omega star, and lambda 2, which is minus alpha minus iota omega star. Now we can write its general solution as yt equals e to the power minus alpha t into a cos omega star t plus b sine omega star t, and we can also write this as e to the power minus alpha t, and it will be a naught cos omega star t minus delta, which we have discussed in the previous example. Now this case, it will represent damped oscillations. This part, a naught into e to the power minus alpha t, will form an envelope. And this cosine part will make an oscillatory motion. So in this case, we'll have these damped oscillations. So essentially this third case is still an oscillatory motion where this amplitude is decreasing according to this envelope a naught e to the power minus alpha t. So these are the three cases possible in case of damped oscillations: overdamping, critical damping, and underdamping. Now there is one more condition possible in oscillations, and that is forced oscillations. In forced oscillations, we'll have my double dash plus cy dash as damping input and plus ky as spring force, and it will be equal to this RT, where RT is called as input or driving force. Now with this RT, there are many cases possible, but of all the cases, the situation is interesting when this input force is a periodic function. So what we'll do is, in our case, we'll assume this driving force as some cosine function. So let it be f naught cos omega t. So now we can write this differential equation as my double dash plus cy dash plus ky, and it will be equal to f naught cos omega t. Now general solution for this equation, my double dash plus cy dash plus ky equals f naught cos omega t is sum of general solution of my double dash plus cy dash plus ky equals 0, which we have already studied in the previous section. And let us say this solution is yh, and then there will be this particular solution when we have this deriving force, and let that solution be yp. We can find this yp by the method of undetermined coefficients, and we know that since it is sinusoidal function, this ypt, it should be of the form a cos omega t plus b sin omega t. Now if we differentiate this, we can write y dash as minus a omega sin omega t plus b omega cos omega t, and y double dash will be minus a omega square cos omega t and minus b omega square sin omega t. Now we substitute it in this equation. We can write m and minus a omega square cos omega t minus b omega square sin omega t plus c, and will be minus a omega sin omega t plus b omega cos omega t plus ky will be a cos omega t plus b sin omega t, and it will be equal to f naught cos omega t. Now what we'll do is we'll take cos omega t together and sin omega t together. So we'll write this as this a into k minus m omega square. So it will be this a into k minus m omega square plus bc omega into cos omega t, and the same way we can write it for sin. So it will be this b into k minus m omega square minus ac omega sin omega t, and it will be equal to f naught cos omega t. Now if we compare cos and sin, then we get two equations which are a into k minus m omega square plus bc omega. It will be equal to f naught and b into k minus m omega square minus ac omega will be equal to 0. Now from here we have to find the value of a and b. So basically these are two linear equations. From the second one we can write b as ac omega upon k minus m omega square, and we'll put it in this first equation. Then it will be a, we'll take common, and it is k minus m omega square plus c square omega square upon k minus m omega square, and it will be equal to f naught. So basically this a, it will be f naught into k minus m omega square upon k minus m omega square whole square plus c square omega square. And if we put a here, we'll get this b as, now in this case k minus m omega square will cancel. So we'll get f naught c omega upon k minus m omega square whole square plus C square omega square. If we take under root K by M as omega naught, which is natural frequency of the system, then we can replace this K with M omega naught square. So now we can write it as A equals F naught M into omega naught square minus omega square upon M square omega naught square minus omega square whole square plus C square omega square, and value of B will be F naught C omega upon M square omega naught square minus omega square whole square plus C square omega square. Now once we have the value of A and B, we can write general solution YT as YHT plus YPT, where YHT is general solution of homogeneous equation and YPT is particular solution of this forced oscillations. And for further analysis, if you want, you can work out condition of resonance in undamped force oscillations, where we'll take C as 0 and we can find damped force oscillation when C is greater than 0. And this is how we study oscillations using second order differential equations.